Now it's time to start looking at some reactions. Now, every type of functional group in organic chemistry has its own particular way of reacting, its own pattern of reactivity. That's what makes it its own functional group. For alkenes, the characteristic type of reaction that they undergo is called an addition. Now, first of all, in general chemistry, we're used to seeing reactions written in a format something like this. So A plus B, let's say going to C plus D. And we'll see some of that as well, but organic reactions are typically written in a slightly different way. So let's look at an example of an addition reaction. First of all, over on the left is the organic compound that's undergoing the reaction. So we can call this various things, but what you'll hear people say is starting material. So people will refer to this as starting material. The substrate, that's another word that people use for this. And both of these mean the organic molecule that's undergoing the reaction. Now, sometimes you'll hear people refer to this as the starting product. That's meaningless. It doesn't mean anything at all. The product is what you get at the end of the reaction, so you can't have a starting product. So instead, you would refer to this properly as the starting material. Now, there's a forward arrow, just like there is in the typical chemical reactions that you saw in Gen Chem. And over and around the arrow are the reagents that you're going to use to react with your substrate. So the reagents that will react with your substrate. Sometimes, although not always, people will include the solvent there as well. So sometimes the solvent is written in this area as well. That is not essential. So in some organic reactions that you'll see, people will include the solvent and others they won't. And that's not something in most cases to worry about. And then over on the right side is the organic product of the reaction. So this is an example of a generic addition reaction. So we added XY across the alkene. And in fact, that's how a chemist would report this if they were talking to another chemist. They would say XY adds across the alkene. What that means is that whatever XY is, X attaches to one of the alkene carbons, Y attaches to the other, and you get a product. So what is this going to look like? What are some specific examples? Well, starting from an alkene, you could treat an alkene with HX. So a hydrogen halide, X being a halogen. X is typically chlorine, bromine, or iodine, so we don't use HF for this reaction. And the reaction itself is called a hydrohalogenation. So we've added HX across the alkene. The result, when you do this, the product is an alkyl halide. So that's one thing you can do. You can convert an alkene to an alkyl halide. You can also convert an alkene to an alcohol through what's called a hydration. So another example of an addition reaction. To do that, there's various conditions that you can use. We'll look at them. One of the ones you could use is water with a catalytic amount of a Bronsted acid. So we'll look into the details of that as we go farther along. And then a third example, you could add a halogen across the double bond. So X2, so chlorine, bromine, or iodine. So each of the alkene carbons gets one of the halogen atoms. That would be called halogenation. And the result in this case, because the halogens are on adjacent or neighboring carbons, we would call this product a vicinal dihalide. Vicinal means neighboring or attached to neighboring carbons. Okay, there are many other addition reactions. These are just a few examples. So let's start looking at some of these addition reactions and look at some mechanisms. We're going to start with a pattern that you'll see crop up in a couple of other reactions here, and that's called electrophilic addition. So let's focus on what's in the box. We're going to treat this alkene with a hydrogen halide, HX. So that could be HCl, HBr, or HI. The result will be an alkyl halide, as we saw on the previous page. And so let's take a look at the mechanism. Now, before we do the mechanism, actually, let's define a couple of terms. So these are terms that we've seen in passing, and now we're going to start using them much, much more frequently. So let's brush the dust off them and bring them back into the fold. A nucleophile is something that donates electron density to something that's typically electron deficient. So that's a nucleophile. A nucleophile reacts with an electrophile. An electrophile is going to be something electron deficient, or that has an area of electron deficiency, like a partial positive charge. So something electron deficient that accepts electron density from a nucleophile. So we're going to see an example of each of these in the mechanism of how this reaction occurs. So we're going to go through this step by step, talk about what's happening in each step, draw an energy diagram, and then make some general observations. So here's the alkene, and let's use HBr for our example, hydrogen halide. And so what happens in the first step is that the alkene pi electrons accept a proton from HBr. So you draw that the way we've drawn any proton transfer. The arrow originates at the thing that's acting as the base. It points to the proton that it's going to accept, and the bond between the proton and the thing that the proton is attached to breaks towards that thing. So this is the proton that's going to get attached to one of the alkene carbons. So there's 2 pi electrons. One of the carbons in the alkene is going to use those 2 pi electrons to form a bond to a proton. That's going to leave the other carbon short electrons. And so the resulting structure looks like this. The carbon on the left used the pi electrons to form the bond. So let's color code the pi electrons. Okay, now they're sigma electrons, but it used that pair of electrons to form a bond to the hydrogen. You notice that it's just one of the pairs of electrons in the double bond. The other carbon lost the electron that it had contributed to the pi bond, and so now it has a positive charge. So that's the first step, and that's the slow step. In the second step, we have a bromide ion that got released when the HBr got attacked in the first step. The bromide ion is going to use one of its lone pair of electrons and form a bond to the carbon with the positive charge. That happens very quickly. So that's the fast step. And so the result is the alkyl halide, in this case, an alkyl bromide. Okay, so looking at this on an energy diagram. Turns out the energy diagram looks a lot like the one we saw when we were reviewing ideas that govern chemical reactions. So you have a two-step mechanism. The first step is rate limiting. This point here is the structure of the carbocation intermediate. And so we start on the left with our reactants, and on the right would be the eventual products. So the alkyl bromide, and then the reactants were the alkene and HBr. Okay, so what happened here? First of all, to remind you, the carbon-carbon pi electrons are the highest energy electrons in the alkene. That means that the highest occupied molecular orbital, or the HOMO, is the CC pi. The alkene uses its pi electrons to accept a proton from HBr. That means it's going to use them to form a bond to a proton from HBr. When the alkene does this, a carbocation forms. So let's write this as when the alkene accepts the proton, a carbocation forms. The carbocation formation is the rate limiting step. And then finally, the bromide ion acts as a nucleophile. It has electron density to share with something that's electron deficient. So it attacks, which in chemistry means forms a bond to, the carbon with the positive charge in the carbocation. That makes the carbocation, because it got attacked by the nucleophile, an electrophile.